My today's topic is based upon ring theory. Ring is another algebraic structure, just like group, and only difference is that in group, we used a non-empty set on which one algebraic operation was defined. In ring, we are going to define two algebraic operations. Okay. The way of defining algebraic operations, two different algebraic operations on a set, on a non-empty set, is nothing new to you. You have already encountered such a scenario in your course curriculum of DSM 101 in the topic of vector spaces, where we discussed about a non-empty set whose elements are formed using the elements of another set. And on the first set, we define a particular algebraic operation. In the second set, we define another algebraic operation and we combine them together. If you can recall the definition of vector space. The similarity between vector space and ring is that both contain non-empty sets. In both the algebraic structures, we define two algebraic operations. The dissimilarity between vector space and ring is that in vector space structure, there are two sets, two non-empty sets. Taking element from one particular set, we build another element from another set. But in ring, there is only one non-empty set. That is the only difference. Okay, so keeping this in mind, I am going to write the definition of ring, and it goes like that. Yeah, okay. A ring R is an algebraic structure which we actually denote by R plus dot, where on R2 operations plus and dot are defined. This plus and this dot are binary operations, but do not consider that this plus is always the operation of addition and this dot is always the operation of multiplication. This could be any two different operations, just like we discussed in the theory of groups, consisting of a non-empty set R together with two binary operations plus and dot. When we say about binary operations, that means we are declaring that the set R with respect to the operations defined is closed. Okay. If we do not declare that plus and dot, the two operations defined on the set, are binary operations, that means you haven't told anything about the closure property of the set. That means suppose you are saying that R1 is a set and you are defining an operation star. Suppose this is your statement. Remember this, listen to me very carefully. Suppose a student is saying that he has a set, a non-empty set R1, on which he has defined an operation star. Then if he wants to prove that this R1 with respect to star is a group or something else, semi-group or suppose any other structure which we can think of, then he first of all, he has to show that if he takes two elements from R1, then this implies that their composition A star B also belongs to R1. Why? Because the student is declaring that this star is just an operation. But suppose there is another student. He is saying that he has a non-empty set R2 on which he is defining a binary operation star prime. If he declares like this, then we don't have to show anything about this property. This property you don't have to show. or don't have to prove. Because whenever you declare that this operation is a binary operation, that means in the definition of binary operation, it is already mentioned that it has to be closed. Okay. First operation that has been defined on the set R will be called, without any loss of generality, it will be called as the operation of addition. And the second operation, which has been defined on the set R, will be known as the operation of multiplication. Okay. These are our actually usual practice. But the beauty of this particular structure is that, and you will be happy to see that first of all, if you want to show that this structure, this set R, is a ring on the basis of these two different operations, first of all, you need to show that this non-empty set R with respect to the operation addition is an abelian group. This is the first criteria. It has to be abelian group. And you know, to prove abelian group, you need to show that the set elements satisfy 5 different properties. Already it is closed with respect to the operation of plus. Associativity must hold. Existence of identity must be there with respect to plus. Existence of inverse must be there with respect to plus. After that, these elements must commute with one another with respect to plus. If it is so, then we call that R plus is an abelian group. I'm not jotting down all the 5 properties over here just to save time. But if you want to show that the set R is a ring, first of all, you need to prove that R plus is an abelian group. And this is, I can say that it is number 1 point that you need to show. Number 2 point is that you need to prove that R dot is a semigroup. What is semigroup? Semigroup is a property where the associativity holds. Suppose we have a group we have a set capital G on which we are defining an operation star 1. Then G star 1 is called semigroup. I'm just reminding you this section. G star 1 is called semigroup if for all A, B, C belonging to G, A star B star C is equal to A star B star C. That's it. No other property is required. And obviously star 1 is a binary operation. So R dot is a semigroup. So with respect to plus, R has to be an abelian group. With respect to dot, R has to be a semigroup. With the property 3, one extra property is implemented over here, that in this particular property, we combine the 2 operations. Here in the property 1, we are only concerned about operation of addition. In property 2, we are concerned only about operation of multiplication. Here we are actually combining the operation of addition and multiplication together, which we actually write as A dot B plus A dot C. And this property, you very well know, it is called the distributive property. And if you think of this structure a little bit, and if you go back in time in your school days, that you will find yourself in, you will find yourself sitting in the class of class 5 or class 6, learning these properties sporadically in different chapters of your mathematics book. Okay, every student of these standards, they know these properties. Only thing they do not know is that they are actually learning a wonderful algebraic structure which is known as ring. Okay. Now, after the mathematicians defined ring, some extra properties were actually introduced in them. They found several examples of rings And a few examples are also there where some extra properties were also involved. So they said they jotted down those properties and they tried to extend their definition a little bit further. What are these properties? See, in the definition of ring, there is nothing is actually mentioned regarding the commutativity of the elements of R with respect to multiplication. So the mathematicians thought, okay, let us introduce one another property, that ring R is called commutative. Ring R is called commutative if with respect to multiplication, the elements commute with one another, and it holds for all the elements present in the set R. This is one definition. Another definition, they are introducing another fact, which is R is said to be having an identity, or in ring theory, we often call it as unity, an identity or unity, if there exists an element, one belonging to R, such that 1 into A is equal to A into 1 is equal to A for all A belonging to R. And suppose we have a set where all these properties starting from A, B, C, and if I call it as property C, I'm calling it, for the sake of the sequence that I have maintained over here, if I call it as D and if I call it as E, suppose a set is there where all these properties from A, B, C, D, E are satisfied, then we shall call this ring as a commutative ring with unity. That structure will be known as commutative ring with unity. Okay, so what mathematicians are actually doing, they are looking around, they are trying to find the physical systems, and slowly, very slowly, from its baby phase to adult phase, they are building some mathematical structures. They are putting extra information, building another structure. They are putting some more information, and they are trying to generalize their previous structure into something else. In this manner, ultimately, they will reach to a particular point. And this ring theory will generate, and gradually you will see that it will progress, and ultimately it will converge to a algebraic structure which is known as field. And you are very much familiar with field because the elements of the vector space are actually formed by taking elements from the field. So you can say that this ring theory is actually falling between group and field. Group is the baby phase and field is the adult phase. This is the, this is the phase this is a teenager phase, you can say. Okay. Now I'm going to give you an example of a set which is a ring. So first of all, I'm going to consider this example. It is my example 1. Let Z I is equal to A plus IB belonging to capital C. In this manner I am writing because it is set of complex number. See the style, I am writing a vertical line over here. Okay, so because there are so many notations in mathematics where we use actually C, not only in complex number. So this type of notation actually mathematicians use, just like I'm using this particular style of writing the set of integers also, to write set of real numbers also. We define two operations, addition and multiplication, on this particular set as follows. A plus IB plus C plus ID is equal to A plus C plus I plus I into B plus D. This is the addition operation, and the multiplication operation is denoted by A plus IB dot C plus ID AC minus BD plus I into BC plus AD. You are actually not unfamiliar with this type of uh, operations. You have done it in complex numbers, and you are actually dealing with a complex number. What is the difference between the set of complex number and this JEDI is that this is the main difference. Just try to point. They look in abstract algebra. One defect is that for which we often find some problems. It's every theorem, every corollary, every result look very similar with some minor changes here and there. And we are often lost in finding which particular statement, what is the difference of this statement with the earlier ones. Okay, so this is the main problem with this type of topics. If you carefully observe this set, actually when we talk about complex numbers, we generally consider this type of elements, but here A and B used to be the real numbers. Okay, so we can consider the complex number as half plus 3/2i. But here you are only supposed to take complex numbers which are formed using the integers and no other set. Okay, so therefore it's a special type of, it's a kind of, you can say it's a subset of the set of complex numbers. Okay, so you have to be very careful what is written in the set. I am not going to show the detail of these calculations because it will just kill time, and you can do it very well. What you need to do is that with respect to this operation plus and dot, okay, for the sake of understanding, let us call this plus as, let us denote this plus by this symbol and this dot by this symbol. Okay, and I can implement this dot over here like A dot C, B dot C, A dot D, B dot D, like this, and this is the plus. Okay, so no, one thing that no, let me write it properly. You will understand. This is the, these are the elements of these are the elements which I have considered from the set of this particular set Zi. Now, if I want to write it, if I want to write the operations, what will I do? According to the operation, I need to write A plus C. Now you see one thing is that this plus operation is not the plus operation which I have defined over here. This plus operation and that plus operation, they are not same. They are different. This plus operation is the usual addition between the set, between the elements of integer set. But when you are constructing the number, the outcome, then you are putting this plus. Okay, so we are writing B plus D in this manner. So this becomes the element. So there is a difference. You have to keep this in mind. Whenever I'm writing AC, I'm multiplying the two integers, AC minus BD. Okay, so here the operation that I'm using is the operation of multiplication in the set of integers. I am multiplying two integers, and then I'm writing this plus, and then this element. Okay, so you have to careful what operations is you are actually applying on which particular element taken from what set. For simplicity, in most of the books, you will get to see that they do not actually differentiate between the symbols. They write all the symbols as plus, as if they are all same, but actually they are not. So to show that this is a ring, you first of all, you have to consider this structure, show that it is an abelian group. Then you need to take this structure and show that it is a semi-group, and then show the distributive property. All this property you can very well identify and you can very well prove, which will guide you to declare that this particular set is the set of uh, is the ring with respect to the operations defined. If you ask me about the additive identity while showing the abelian group, 0 into I0 is the, that much I can write. It is the additive identity in this particular case. And if I have an element like, if I consider, this is point number 1. Point number 2 is that if I consider an element like a plus ib, so with respect to that, its inverse, additive inverse will be minus a plus I into minus b, so that we can call it as minus z, so that z plus minus z becomes 0 plus I0. Okay, and the element which in the definition you will see that in definition E you will find that this type of element is also there. If I try to look at the operation E with whether it is being satisfied or not, so can I find any number, any element in the set R like 1 which will be having this property as mentioned in definition E? You will find that extra point that we can consider one such operation like by taking 1 plus I0 as the element of Zi. Okay, and if I multiply the number a plus ib with 1 plus I0 with the operation, I'm not using the symbol over here right now, dot. Okay, but just for the sake of saving time, we will find that this will be exactly equal to a plus ib. Okay, and therefore this property E will actually be satisfied over here. Not only that, you will also be able to show property D if you consider two elements Z1 and Z2 from this particular set. You will very well be able to show that Z1 and Z2, they are multiplied in this manner, is exactly same as Z2 and Z1. All this you can verify by yourself whenever you get time. And the operations, all the operations starting from A, B, C, D, E, all these will show you, lead you to the fact that the set Zi is the commutative ring with unity with respect to the two operations defined. It's a commutative ring with unity with respect to the two operations defined. Or you can write it in this manner. Simply, if you don't want to write all these lines, you can write Zi plus and dot. This triplet is a commutative ring with unity. Commutative ring with unity. Okay. And this particular ring, this particular special ring in this mathematics community is a special example, and the mathematicians call this particular set as ring of Gaussian integers. These are not just the integers, these are called the Gaussian integers. So, and the set is actually known as the ring of Gaussian integers. So remember this example, it's very important. So ring of Gaussian integers is a commutative ring with unity. Ring of Gaussian integers is a commutative ring with unity. Another example which I can set, you take the screenshot of this page. Another example that I can consider over here, this example is also known to you from from some other perspective, that if we consider the set Zn, which is the set of integers modulo n, where n is a positive integer. Okay, n is a positive integer, and we define operations plus and dot on Zn by the class A plus class B is equal to class of A plus B, class A dot class B is equal to class AB for all classes A and B belonging to this set Zn. Then you can easily show that this particular set Zn with respect to plus and dot as defined is also a commutative ring with unity. And this particular commutative ring actually, unfortunately, is actually not having a special name like Gaussian integers. Okay, so not always we have names. This is just an example which I'm actually citing over here. I think that when I write class A, actually I think that you can recall the definition of classes, because we studied this particular elements, class A and class B. If I want to remind you, we studied it in the chapter of congruence relation. Congruence relation, which is a kind of equivalence relation. When we did that particular topic in unit 1, we discussed this sort of elements. Okay. So I'm not going to the details of the proof of this particular result. You can verify by yourself. It is an example. I'm considering this as homework you are supposed to do. Then we can set another example, example 3. Suppose we are considering the set G with respect to the operation plus. Suppose this particular structure be an abelian group. Okay. Written additively. We define an operation such that when we consider A and B, the two elements, A dot B becomes 0 for all A, B belonging to G, where 0 is the identity element. 0 is the identity element of the group capital G. Then such a ring G plus dot, you can very well show that it is a ring, and is called null ring. This ring is called a null ring. When we write that G plus is an abelian group with respect to the operation addition, which is written additively, that means the usual operation of addition, the way it is defined. Suppose you are considering a group where plus is not usual operation of addition, then also it will this result is applicable. It is not like always you have to consider the usual operation of addition. By usual operation of addition, I actually mean the operation of addition that we use in number theory. Other operation of additions are also there. Matrix theory, matrices. When we add two matrices, that addition is not the usual operation of addition. Suppose you can construct any capital G, any group where a particular addition operation is defined. Okay. But in that particular group, if you choose any two elements and their composition with respect to the multiplication always results in 0. 0 is the additive identity of that group. Then such a structure is called ring, and this ring is called the null ring. That is a very important fact. One another example before I conclude my first session of today's class is the following. Example 4. Let M and R be the set of all n by n real matrices. N by n real matrices where n belonging to capital N. Then M and R is the set of real numbers, is closed under usual addition and multiplication of matrices. Why? Because if you consider two matrices, and if you add them or multiply them, the result is also a matrix. Okay. And we know how these addition and multiplication operation on matrices are defined. Then you can easily show that this particular set of all n cross n matrices with the operation plus and dot, this becomes your ring. Simply ring. It will not be a commutative ring because multiplication of two matrices is not commutative. And since the multiplication of two matrices is not commutative, that's why in quantum mechanics we say that position and velocity cannot be measured accurately. Because why do we say this? To position, to the physical to the observable position, we have an operator. Every operator has a matrix representation. So position has a matrix representation. Velocity of the particle, velocity, with respect to velocity, the observable velocity, we have an operator. To every operator, there is a matrix representation. So velocity has a matrix representation. When we multiply the position by the velocity matrix, position matrix by the velocity matrix from the right hand side. So that means what? We are actually trying to find the position first and then velocity, which is not same as when we multiply the velocity matrix by the position matrix from the right hand side. That means we are trying to find out the velocity and then position. Because this operation is not commutative, therefore its outcome is the Heisenberg's uncertainty principle. And therefore, initially, when Heisenberg actually defined quantum mechanics, he didn't name it as quantum mechanics, he named it as matrix mechanics. And therefore, this wonderful result he deduced, for which he got the Nobel Prize. And nowadays, this high uncertainty principle plays a very fundamental and important role in the topic of quantum computing. Okay, so here I'm not writing that MNR plus dot is a commutative ring with unity. Here I'm only writing that it is a ring. So all these examples you need to work out by yourself at home whenever you get time. We are going to discuss the remaining of the topics in the second session.